Hello. Yeah. So welcome to new video. Some of you guys asked me to show a video how to get a dispersion relation for any structure on using CST. So in this short video, I'm going to briefly show the steps to do this. So first, I opened CST, we are going to choose a template here. So to run Eigenmode solution, we need to select let's say microwave RF optics, and then we choose periodic structure. Here it's in general 2D, but the one we are going to do, we are just enforce periodic boundary in just one direction. Yeah, we can just use draw unit cell. So we are going to select this part. And yeah, we are interested to find the dispersion relation. So this is the kind of solver we are looking for. It's Eigenmode solver. I'm going to keep the units here as a default. And this should create a template that is designed to run CST simulation. For simplicity, I'm going just to simulate just rectangular waveguide with some corrugations. Before starting the simulation, I'm going just to define some parameters here, like A, which is, let's say, 17 millimeter. So this is the dimension for the rectangular waveguide, and B, let's say 8 millimeter. And the period of the structure, let's say the period is 50 millimeters. And let's say W, which is the width of the corrugation. So let's say it's 10, for example. And let's say H is the height of the corrugation. Let's say it is also 10 millimeter. So I'm going to start to draw my structure. This should be straightforward. I'm going to draw the metal wall of the rectangular waveguide. And so let's define here thickness T, let's say is 1 millimeter. So this is the thickness of the metal. So to draw this rectangular waveguide, I'm going to draw just a solid structure. Then I'm going to subtract the inner filling. So I'm going to do it symmetric. That's why it's going to be from A over 2 negative T. So it's because I need to add the external thickness to A over 2 plus T. For Y, it's going to be from, let's say, negative V over 2 negative T to B over 2 plus T. For Z, I'm also going to make it symmetric around Z for simplicity. That's why I'm going to do it from negative period over 2 to period over 2. And I'm going to choose this material to be perfect electric conductor PEC. Just let's preview this. This should be the structure, but yeah, we need to remove the inner filling here, just to make the filling of the rectangular waveguide. So I'm going to draw another rectangular block, but this time I will not add the thickness. So it's going to be from negative A over 2 to negative V over 2 to B over 2, from negative period over 2 to period over 2. And here we go. So this is the inner one. Fine, I'm going just to subtract the two geometries. And here we go. So this is the rectangular waveguide shape. So this one is uniform. So just to study general structure that is periodic, let's just make a cut here just to see what's inside. I'm going to add a corrugation here, a rectangular corrugation here with a width of here W and height of 10. And it should take the whole dimension in X direction. So that's why it's going to be A is negative from A over 2 to A over 2. For the Y, it's going to be from 0 to the height we are interested in. And for the Z, it's going to be from negative W over 2 to W over 2. And this should be, okay, so for the H, yeah, for the H, it should be actually smaller. So let's press OK for the moment. And we go for the H. We just make it few millimeters, right? Maybe 3 millimeters. And here we go. Yeah. Oh, yeah, my bad. Yeah. So for the Y, because if we are interested to start from this one, this Y should be negative P over 2. And the maximum height should be negative P over 2 plus H. And here we go. Yeah, this is the right one. Yeah. And finally, this should be the structure we have. It's like a rectangular waveguide with corrugation. So what we can do, we can add this structure using Boolean by making add here. So now they are just one structure, and this should be like the geometry. So because I did not define the filling material here, that's why we need to go to background and make sure the background is normal, which is just like vacuum. So that's why any material that is not defined in the space here will be treated as just vacuum. And for Eigenmode solver, we don't need to specify the frequency, we just need to specify the minimum, the maximum. Let's say the maximum is 100 gig, because I should have some feeling of the number. Okay, so let's go to the boundary, which is a tricky part. Okay, so the template here is designed for 2D periodic structure. We are just interested to make like periodic structure in Z. That's why we're gonna make X and Y as PEC, because this is already a metal, and that's why we don't have extension of the waveguide in X and Y, and this like metal we already use is already fine. And for Y, for Z, we're gonna use periodic boundary. And to have like condition, we need to go to the phase here and add the phase we want, which is negative phase underscore Z, for example. This is gonna be a new parameter. And I'm going to define this value as Z at 0, for example. Let's say I'm interested to get the cutoff at the moment. And we are all set. We just need here to select the number of modes. I usually prefer like plotting 3 modes. I'm going just to run the simulation for the moment, just to get this like single point. So the way Eigenmode solution works, you give it a phase, it gives you a frequency. It doesn't work the opposite way. So you put some phase here. For example, you put negative phase, which is from the maximum Z to the lower Z. So this means that actually the Eigenmode solution is looking for electric field that is periodic in Z with just a periodic boundary of a phase delay of negative phase Z here, which you already added here. So like the output of the Eigenmode solution are 2 things. First, it gives you the frequency that satisfies this phase and how the profile of the mode look like, how the 3D electric field and magnetic field distribution look like here. And because we selected 3 modes, the Eigenmode solution gonna find basically 3 modes. So like CST usually is using like adaptive mesh. That's why it keep going here using adaptive meshing. We can check like what is going on versus time. It's now at the first pass. It keep repeating different passes until reach some error that is specified as a threshold. So now like it didn't converge yet. So we'll just have to wait. And after I show you just like one operating point, I'm going to show you, okay, now you want to plot like a dispersion relation, right? You want to see how the phase basically is KD or K times period look like versus frequency, how you do this. Yeah, so let's show the output first. Here we have mode frequency, we have mode 1, and we have mode 2, mode 3. If I plot them together, this is actually the cutoff frequency of different modes. And 1, 2, 3 are basically Eigenmode solution. You just arrange the waves or arrange the modes in just ascending order of K, and you don't have information about how this field look like unless you go to field here. I'm going to plot the electric field. I usually prefer like contour, and I'm gonna plot field on like field on plane, and let's say we're gonna animate, and this actually at the cutoff frequency, like you don't have a propagation, right? And as we can see here, this is, for example, this one mode, and we can also see how the field look like in Y, and let's say we make Z here. So what we can do, we can increase this, for example. So this is basically TE10 because the field doesn't change a lot in X. It's just like it just has one peak across X and it's uniform in Y. And this is the second mode. This is the third mode. Okay, so now if you want to plot the dispersion relation, you need to add parametric sweep here. You're gonna delete the default sweep here and add your own sweep here. You choose the parameter you want to sweep, which is the phase of Z. Let's say I'm going to sweep it from 0 to 180 just to cover half radium zone. The other one should be like symmetric because like the structure is periodic. And let's say I'm going to add, let's say 13 samples here. And need to store this. So actually like this is equivalent to running multiple points for the Eigenmode solution. And if you go here, yeah, now we have this point just for phase equals 0. What we do, we're gonna find the other point and it keep going until like we have like a dispersion curve. So I'm going just to wait maybe for 1 point or 2 point to show like 2 extra points just to show you the curve. And this can be applied to any periodic structure. You just will have to repeat the same step, except that you draw your own like structure. You can draw like serpentine waveguide, or like you can draw helix waveguide. You can draw whatever periodic structure. It's just important to mention the structure should be periodic, and what we are drawing here is just a unit cell. So if you think about the actual structure, it should be just a repetition of this one, but because this is how Eigenmode solvers work, you just give it a 1 unit cell. And unit cell is basically the minimum geometry that is repeated, so that if you just know this geometry and you keep repeating it, for example, here in Z direction, you're gonna basically construct the whole structure. So if you think about this structure, if you keep repeating it, it's gonna be just like rectangular waveguide with periodic grating made of metal here, for example. I'm waiting just for this extra point. If you see here, this parametric sweep showing 2 out of 13, because 1 is already done when I initially run the solver without parametric sweep. That's why it's smart enough to know which points you already run. And also you can see here the total number of tetrahedrons. These are the cells, the mesh cells used. Like I can make view here, and you're gonna see what is the segmentation used to construct like to numerically solve this one. But I usually trust the default meshing. If you don't have trust on the default meshing, you need to go to properties here, and you need to add extra feature. To if you have like, for example, a structure with small features. And I mean by small feature with respect to the wavelength, because the default here is a segmentation with respect to the wavelength. Okay, now I go to mode 1, still like solving for the second point. And the second point you see here now it's 15. So the software already solved 0, and now it's solving 15, and it will keep going until like it just like, yeah, the second point, I think it's almost done here. Okay, now you see just like a dispersion if you consider just like very small range for phase. But if you keep drawing this, for example, it's gonna go like as if it constructs a dispersion. So what is the Y here? Y is the frequency. X here is a phase across one period. And you can think about this as a wave number times D, or times period. So this is actually KD, or K period, and the Y here is frequency. And this is actually the cutoff frequency. So if you keep running this, it should generate a dispersion curve. And if you plot the whole one, you're gonna see all the modes. And just to know which mode correspond to, you need to figure out how the feed look like from the 2D mode. Yeah. So thanks for watching. Thank you so much. And yeah, see you next video.